So hello, everybody, and welcome to this week's SEDS Online webinar. As always, we'd like to thank our sponsors from IAS, which allows us to offer all of these resources free of charge. This includes our recorded lectures, our learning tools, and even virtual field trips. So make sure you take a look at our website to see what is new. Today's lecture is by Dr. Chris Stevenson, who is a quantitative sedimentologist at the University of Liverpool. Dr. Stevenson got his master's degree at the University of Leeds and his PhD degree from the University of Southampton. His research interests include understanding submarine landslides, or anything that moves downhill. So I'll give you the floor and let you take it away.
Thanks very much, Simone. So, yes, thanks very much for inviting me to give this talk today. And I'm going to be talking about meteorites and mass extinctions. So a topic that's quite different and apart from my usual patter of turbidites. And this is work that I've been slow boiling with Matt Pankhurst and Bev Goldwell over the past sort of 8 years or so. So it's a slow burner, this one. And what I hope to convince you of over this presentation is that when it comes to meteorites and mass extinctions, size doesn't matter. And we'll no doubt have a good discussion at the end with people being fairly convinced of this fact. Okay, so this story covers a range of different topics and a range of different types of analysis and data. And so it's going to feel a bit like one of those Poirot murder mysteries where you don't really understand the significance of particular lines of evidence until you see the complete picture at the end. So just bear with me if some of the segues between topics are a bit jarring, okay, or they don't necessarily make sense. Why did you do that? Well, it'll make sense when we bring it together at the end, okay? So what we're going to be doing today is we're going to be talking about meteorite impacts and their relationship to mass extinction events. We're then going to talk about how the mineralogy of the rocks these meteorites hit is actually the important bit when we're considering their effects on the biosphere. We're then going to talk about cloud microphysics and the composition of clouds, and then in turn how this influences and modulates global climate. So we're going to go on a bit of a journey, so let's kick things off. So, meteorite impacts. Meteorites have been bombarding the planet over the geological history of the Earth. They're repeated phenomena that have affected or variably affected the evolution of multicellular life across the last 600 million years or so. Now, some of them are associated with mass extinction events. The most famous of which, of course, is the end Cretaceous Chicxulub Club impact in the Gulf of Mexico that resulted in the extinction of the non-avian dinosaurs. Now, when it comes to meteorite impacts, what kills the biosphere? What generates these severe mass extinctions? Well, the kill mechanism is something called impact winter. And this is a process by which a meteorite comes in, hits the Earth, and then exhumes rather forcibly the target rocks that it's hit, and throws up loads of dust, debris, and material into the atmosphere, and high into the atmosphere, stratosphere. This material then gets dispersed around the globe, and then it fundamentally affects the climate. It blocks out incoming solar radiation, and this causes global cooling and reduced light levels on the Earth's surface, which fundamentally affects the photosynthetic organisms and cuts the legs out of our ecosystems. So that is what has been the kind of the established paradigm of why big meteorite impacts kill off loads of stuff when they occur. Now, in this impact winter scenario, it should be an instant kill mechanism, geologically speaking. Okay, so what we should see is in the geological record very abrupt extinction events associated with meteorite impacts. In addition, there should be a nice correlation between impact size and extinction intensity, because the bigger the impact, the worse that impact winter is going to be. Okay, so what we did is we went looking for this correlation, and we used the most recent database of meteorite impact stratigraphy over the last 600 million years of multicellular life. So what we have here on the graph is, on the x-axis, 600 million years ago on the left, and then present day on the right. And then on the y-axis, we've got our crater diameter from about 10 kilometers across all the way up to 85 kilometers across for our Jigsaw Club, the big monstrous impact. So the circles are also scaled to impact size. So the bigger the circle, the bigger the impact. All right. So what we can see is we've got a nice array of about 33 or so impacts to correlate with our fossil record through geological time. So we then compare this stratigraphy to the fossil record. Now, the record we've used is the marine fossil record, because it's the most consistent through geological time from 600 million years to present day. And it provides the highest level of biostratigraphic resolution, 167 sort of substages. So this allows us to give the best possible chance of things not working or working really nicely. Okay, so what we can see is, I wonder if I can. Don't worry about it. Okay. So what we can see is that on the bottom graph here, our kind of wiggly black line with our stalactites coming down represents our extinction intensity. Okay, so our baseline of 0 extinction intensity sits at the flat line, and then the stalactites hanging down represents increased rates of extinction intensity, with some notable mass extinctions highlighted: the end Permian and the end Cretaceous, with our reptilian overlords being wiped out. Okay, now what you might be able to pick out is that some of our large impacts, the Jigsaw Club, for example, do correlate with a mass extinction event, but others don't. And in fact, the fourth largest impact, the Meteoritic, that's 50 kilometers in diameter, is associated with background extinction rates. So no increased extinction at all. And that's pretty weird, right? So when we run the stats on here, we find no correlation between meteorite impacts themselves and extinction intensity increases. Furthermore, when we look at impact size and extinction intensity, we don't find a correlation either. So there is no correlation between our impact size and the extinction intensity. Let me show it a different way. Here's a different plot showing the same thing. I've taken the 13 best constrained impacts, meteorite impacts, and plotted them in terms of their size and extinction intensity. In this case, as a function of percentage change from the previous substage. So what you can see is that anything in pink here is a mass extinction, and anything in blue is background extinction intensities. So let's take our Jigsaw Club impact. Yep, it's big and it causes a mass extinction, or at least it's associated with one. But then we've got smaller impacts in the Eocene and mid-Miocene that are associated with mass extinctions. If we look at the fourth and fifth largest impacts in our meteorite record, they're associated with stable and even diversifying ecosystems. So, what's going on? We've got no correlation here between meteorite impacts and extinction rates. The impact winter kill mechanism should be associated with size of impact, but we find no correlation between size of impact and how deadly the impact is on the biosphere. So, over the years, we explored the idea that it might not be the impact itself that's the problem, but rather it might be the mineralogy of the rocks these meteorites end up hitting on the Earth's surface. And so Bev and Matt in 2019 published a really nice paper in the Johns Hopkins London, where they looked into this by reconstructing the aerial distribution and thicknesses of the impact ejector blankets associated with all of the meteorite impacts over the last 600 million years, above 10 kilometers in diameter. So any meteorite that made a dent, what they did is they applied a numerical model to use that greater diameter as a proxy for how much volume of material had been exhumed, and then drew progressively wider concentric rings of depositional isopachs to represent the deposition of the ejector blanket from each impact. Now, in addition to that, they also estimated or calculated the amount of potassium feldspar that each ejector blanket contained, and in turn estimated how much potassium feldspar then covered the surface of the planet after each meteorite impact. Okay, and they grouped them into K-feldspar rich and K-feldspar poor ejector blankets. So, don't get too hung up on whether these reconstructions are accurate in terms of their exact distributions and so forth. The key thing that this analysis allows us to do is to compare the same analysis between meteorite impacts. And that allows us to compare the mineralogy and in the K-feldspar content of each ejector blanket over the past 600 million years, which is very cool. So let's go back to our figure 1, where we're looking at meteorite impact stratigraphy and our extinction record. Now, I'm going to tell you that our colours are a proxy for how much potassium feldspar was in each ejector blanket after the meteorite impacts. The warmer the colour, the more potassium feldspar is in the ejector blanket, and the more potassium feldspar was covering the surface of the planet. Okay, so what we see now is that our extinction intensity graph at the bottom starts to, I've coloured it in to match the potassium feldspar content of the meteorite ejector blanket. So what we see immediately is that our spikes, our mass extinction episodes, are typically coloured pink, which means they are associated or coincident with a meteorite ejector blanket that's rich in potassium feldspar. Conversely, meteorite impact ejector blankets that are K-feldspar deficient are associated with periods of ecological stability, and you can see those coloured in blue. So you don't need to take my word for it though. You can, when we run the stats on this, the correlation is pretty remarkable. Here's a visualization of the correlation, whereby the drain tracks that you see from left to right represents the biostratigraphic substages from about 600 million years on the left through to present day on the right. And that includes 167 substages through geological time. The dark black lines, the thick black lines, are the 23 mass extinction episodes that are recorded through the fossil record. Those include the big six. And then our coloured arrows going down and up onto that train track are our meteorite impact events. Okay. Totaling about 32, give or take, constraints on age ranges. So for potassium-rich ejector blankets, every single one of them coincides with or tightly overlaps a mass extinction episode. Every single one. Whereas our K-feldspar poor ejector blankets correlate with or correlate exclusively with periods of ecological stability. So what this statistical test essentially means is there is a one-to-one correlation between ejector blankets that are rich in potassium feldspar and mass extinctions. Every time this happens, there's a mass extinction. Second, there's a negative correlation between K-feldspar deficient ejector blankets and insignificant changes in extinction intensity. So this is a really nice correlation where we have a positive correlation with extinction intensity, but also a negative correlation with background extinction intensities. And potassium feldspar is the key parameter that discriminates. Let's look again at this, plot, whereby now you can look at it with slightly different eyes, whereby the warmer colours are increasing levels of potassium feldspar across the Earth's surface from the ejector blankets, and then the colder colours are the K-feldspar deficient impact ejector blankets. And rather than size, you can see that it's K-feldspar that cleanly separates what meteorites kill and what meteorites don't. And that's pretty cool, right? So the take-home message from that section is it's rock mineralogy that matters, and in particular, how much potassium feldspar is contained within those rocks. So, hang on, Chris. Potassium feldspar is hardly the most toxic mineral we've got on the planet, and I'd agree with you. It's basically benign. And so that raises the question, how can potassium feldspar be so destructive on a global scale? It's weird. And to understand that, we need to talk about clouds. So clouds are composed of either water droplets or ice particles. Water droplet clouds form at relatively low altitudes and at relatively warmer temperatures. Ice particles form at much lower temperatures and therefore at much higher altitudes. So the critical temperature for ice formation from water vapor in the atmosphere is about minus 36 degrees. Now, when you introduce particles into the atmosphere, these can become catalysts for changing that temperature for ice nucleation. So ice nucleating aerosols can change where and how clouds form. Potassium feldspar is the most powerful ice nucleating aerosol we know about, and it profoundly changes the ice nucleation point for clouds from -36 all the way up to -18 degrees C. It's a massive change. And so what that means is that ice can form at warmer temperatures and at lower altitudes. And this gives rise to mixed phase clouds at lower altitudes. And indeed, anything above that would become more and more icy. Okay, so, okay, Chris, that's great. Why is that important from a climate perspective? Well, the composition of clouds dictates how reflective they are to incoming solar radiation. So, the more icy a cloud is, the more radiation it lets through, which is essentially a reduction in the cloud's albedo effect. So, for our ice-dominated high-altitude clouds, they let in lots of solar radiation and affect a small warming force on the global climate. Mixed phase clouds have a small amount of reflectivity, but still let in lots of solar radiation and warm the planet. It's only when we get to water droplet clouds that have a high albedo and they affect a cooling force on the global climate. So, cloud albedo is a fundamental agent in modulating the atmosphere and how it buffers global warming or cooling forces. If we reduce the cloud albedo through making it more icy, we will affect a warmer planet from direct solar heating forces. Introducing more icy cloud has a knock-on effect. As the planet warms, there's a cloud feedback mechanism whereby more evaporation increases cloud cover and increases the amount of albedo which reflects more solar radiation and cools the planet. However, if that cloud that's being made in response to global warming is predominantly icy and affected by our potassium feldspar, then it's still going to let in lots of solar radiation. So rather than cooling the planet, that feedback is suppressed and we're actually going to get an atmosphere that warms faster and to higher temperatures for a given greenhouse gas concentration. Okay, so lots of potassium feldspar in the atmosphere can potentially have serious consequences for global climate. So let's put this together in a flowchart model to understand how all these things interact. Let's start with our global climate in its equilibrium state, whereby particles in the atmosphere don't really affect cloud dynamics. Low altitude clouds are water droplet dominated, and our high altitude clouds are icy. And so we have a nice balance of high albedo, low albedo clouds. We have our meteorite impact. This generates loads of dust that's thrown into the atmosphere, generating our impact winter. This situation is a short-lived climate phenomenon. And if our impact ejector material is low in potassium feldspar, that impact winter ejector blanket will settle out over several months or a year, and those dust particles won't affect cloud dynamics appreciably. And so we get a reversion back to our climate equilibrium state. No harm, no foul. However, if our material, our ejector material, is rich in potassium feldspar, as that ejector blanket settles out onto the Earth's surface, the lower atmosphere, the troposphere, will be subject to a high proportion of potassium feldspar mineral aerosols, which will profoundly affect the composition of clouds and change their albedo to incoming solar radiation. This will generate global warming and a range of knock-on factors. Moreover, these effects on cloud dynamics and the atmosphere will progressively diminish over time as weathering processes chemically transform our potassium feldspar back into clay particles. So these weathering processes will diminish this mechanism progressively over tens of thousands, millions of years. Now, I can hear you all on your mutes at home. That's great, Chris, but you still haven't told us a replacement kill mechanism for the biosphere. What is it that kills off life? Well, this really is the next step in this work, to try and explore how a profound change in atmospheric function can have cascading and catastrophic effects for the biosphere. And there's a range of possibilities. We could get potential extreme UV exposure, such as being recently proposed for the Devonian mass extinction. Icy clouds have much shorter lifespans than rainwater clouds, and they rain out much faster. So we might have completely changed rainfall patterns and drier continental interiors. This might be particularly problematic for, the supercontinent mass extinctions. And our climate is much more sensitive to warming from external forces, such as large igneous provinces. So there's a range of options, and I don't know why it's done that. Weird. So homing in on large igneous provinces, as an example, large igneous provinces only variably correlates with extinction or mass extinctions through time. And similar to our meteorite story, the volume of material erupted from these events does not correlate with the severity of extinction. However, it's curious that every single large igneous province that does coincide with a mass extinction event also has a coincident potassium feldspar rich ejecta blanket to go with it. So it's possible that these phenomena are interacting to produce catastrophic effects on the biosphere that we've previously not really even considered, which I think is pretty neat, right? So, to summarize, I want you to go away rethinking meteorite impacts and how they work. First, size doesn't matter. And I would argue actually that the impact itself, whilst devastating locally, doesn't really matter on a global scale. Rather, it is the exhumation of terrestrial rocks and the deposition of an ejecta blanket rich in potassium feldspar that is a killer. So it's the mineralogy of this ejecta blanket rather than the impact itself that is the problem for our planet. And this is because mineral aerosols from the ejecta blanket profoundly affect our cloud composition, turning clouds icy, which allows lots of solar radiation to come in, warming the planet, and then as a secondary effect to make the global climate system more sensitive to external forces on heating. So that would include greenhouse gas emissions from volcanic activity, but also variations in solar radiation from Milankovitch cyclicity, for example. And so this work really opens up a lot of possibilities of the existing kill mechanisms that have been proposed in the literature interacting with our model to produce these severe extinction events that we see periodically through the rock record. So thanks very much for listening, and very happy to take any questions.
All right, thank you very much. That was super interesting. Certainly something I've never really considered. So if you have any questions for Chris, the chat is now open. So make sure you type your questions into the chat and share it with everybody, and make sure to mention where you're watching from, and we can ask those questions to Chris. But while we're waiting for your questions, I have one. So it seems like location is sort of a critical factor for where these meteorites are hitting.
Yeah.
So do we see more on land-based ones would cause the mass extinctions than meteorites that hit the oceans?
Well, so not really, but so the impact location is serendipitous. So the key is, does the impact ejecta blanket settle on land or water? So if it settles in the ocean, it cannot be recycled into the atmosphere as dust. But if it gets distributed across the land, then that dust is readily available to be entrained into the atmosphere and the lower troposphere to be effective as ice nucleating particles. So it's not that hitting the water or the land is critical, but it's where the ejector blanket ends up. Because if you think about it, the speed at which these things are going, even a couple of kilometers of water depth isn't going to do anything to slow it down. Not really. So, but yeah, it's a good question. God, my voice is going, sorry.
I can totally understand you. So we have a comment from Jacko. He says, great talk, Chris. One of the clearest SEDS Online's talk that he's attended.
I try my best.
Your voice is not a problem.
Try my best.
So the chat is actually now open. But I have another question. Does these mixed phase clouds, do they help to trap the greenhouse gases as well to sort of increase that warming effect?
Yeah, they do. So the warming or cooling effect for clouds depends on the wavelength of radiation. So shortwave radiation from the sun gets blocked out very easily by water droplets, but gets let through by ice particles. However, so that's a warming effect. But long wave radiation, infrared radiation, is emitted from the Earth's surface, and this passes through water droplets quite well, but is blocked by ice particles. So mixed phase cloud is a bit of a double whammy because it blocks lots of the shortwave radiation. Lets it through, but then it also blocks the long wave radiation. So it's like a double warming factor. So
excellent.
Yeah.
All right. We have a question from Valentine. Hi, Chris. Super cool presentation. Love the quality of the graphs. I have to apologize. I missed the first 5 minutes of your presentation, and I might have missed this. Where is your impact location at the end of the Permian mass extinction?
Oh, God, off the top of my head, I don't know. But if you look at the Caldwell and Pankhurst paper from 2019, the John Sock of London, it has all of the locations and all of the modelled impact ejector blankets to go with it. So the thing is that back through geological time, you have to rearrange the continents. So the impact location is obviously not where it is now. It's the rearranging of the continents where it is then. So it's much easier for me to describe, like using a map and pointing at it, a paleogeographic map. So I'd recommend reading the Caldwell and Pankhurst 2019 paper for that.
Our next question is from Stephanie in Denmark. Thanks for the talk. How precise is your temporal correlation between mass extinction events and the impact events?
So that is the $1 million question. And there are 44 meteorite impacts over the last 600 million years that are above the threshold of 10 kilometers diameter craters. So they made a dent. Of those 44, only 32 of them have age precision that is within a single substage or 2 or 3 substages, biological, biostratigraphical substages. So the 13, we have 13 examples where age precision of the impact is within a geological substage, which means it's within the same biostratigraphic episode as the extinction event. So that's as close as you can get with correlating the meteorite with the biological effects. And of those 13, 7 of them correlate with the mass extinction, and then 6 of them do not. And that's a 1-for-1 with potassium feldspar and no potassium feldspar in the ejector blanket.
Pretty good precision.
Yeah, yes.
Our next question is from Nina in Germany. Very interesting and clear talk. What is the reason that potassium feldspar specifically has this effect? Is it the particle size related? Is it particle size related or crystal structure related? I'm completely unfamiliar with how this all works, or maybe I missed the explanation.
No, you and me both. So mineral aerosols and their effect on ice nucleation is a frontier field in climate modeling and climate science. Okay, so exactly why potassium feldspar is so powerful an ice nucleating particle is not really understood. But the initial ideas around it are that it's something to do with the crystal structure. And because different polymorphs of potassium feldspar have different catalyzing temperatures. So perfite, for example, is the strongest mineral aerosol in terms of its ability to drop the temperature. Oh, sorry, raise the temperature. But other potassium feldspar mineral assemblages have similar but variable effects. So my guess is it would be the crystal structure rather than the size of the particle or anything else like that.
Okay. Our next question is from Jacko in Wales. Doesn't size matter in that smaller meteorites store up less potassium feldspar, even if the potassium feldspar content in the rocks is the same? In other words, how much potassium feldspar flux is needed to change climate?
Right, so there are two measures of the amount of potassium feldspar. The first is in that top half of the graph with the big bubbles, where we make estimates of how much potassium feldspar was in the ejected material. But then, in the bottom half, we make an estimate of the volume of potassium feldspar that covers the surface of the Earth after that ejector blanket has been deposited. So this measure, which is we call the potassium feldspar factor, is basically timesing together the proportion of potassium feldspar in the rocks by the volume of the material excavated. And so that gives you the volume of potassium feldspar on the surface of the planet after the impact. So you're exactly right, Jacko. So that's what our analysis does. It accounts for size and the concentration of potassium feldspar in the excavated rocks to produce this K-feldspar factor. And how much, I'm not going to go there because I think we need better modelling of the impact ejector blankets to be more quantitative rather than comparative between impacts. So that's how I would answer that. But that is a brilliant question and one that I think is relevant for modern day climate modelling. You know, how much K-feldspar mineral flux is needed to screw up the planet. It's pretty important.
Mm-hmm. Our next question is from Stephen in Derby. Hi, fabulous presentation, a great story. Sorry for my ignorance, but I am pretty certain that I have heard or read that impacts into evaporites are also pretty catastrophic. from the point of view of sulfur inputs into the atmosphere. Do you think this model is also valid?
Yeah, so the those models of looking at sulfur compounds that generate acid rain and toxic air to breathe, think that sort of stuff. Of course, they are bad. They are really bad effects, but they are likely to be short term and they're likely to be localized around the site of the impact. So those models are, I would argue, secondary to the argument that I put forward here, that the impact does cause damage and it does cause problems, but those effects are going to be local and related to the site of the impact. Jigsaw clump being really bad, vaporizing material thousands of kilometers either side of the impact, that sort of stuff. But if these kill mechanisms that have been proposed with sulfur and evaporites were so effective, we would see a persistent response in the fossil record of instant kill. And we don't. We see variable expressions of extinction, stepped, abrupt, or gradual. So I think our model makes more sense as a long-term climate destabilizing force that allows the biosphere to be destroyed over time or abruptly or whatever. So they're valid, but I think secondary importance.
All right. Our next question is from Jordi in Barcelona. Great talk, Chris. Very interesting. I have a question. Do you think that the formation of potassium feldspar rich ejecta blanket is associated with the composition of the meteorite, the composition of the rock that received the impact, or maybe the formation is directly associated with igneous activity? Thanks for your answer.
So from the mineralogical analysis of meteorites that have been recovered, they don't tend to contain much potassium feldspar, but it's not to rule it out, because these things get vaporized when they hit the planet. The big ones do anyway. So we think that it comes from the rocks that the meteorite hits. So the terrestrial rocks that are there, they then get clobbered. So our analysis is based on the mineral content of those terrestrial rocks. And what we see is that from that analysis alone, we get that nice clear discrimination between potassium feldspar rich and poor ejecta blankets. So the next step would be to go out there and start doing some mineralogical analysis on ejecta blankets to start to see if these things really are or really contain these sorts of minerals. But we certainly think it's the composition of the impact rocks rather than anything else. Yeah.
That'll be fun field work, going to check all those craters.
Yeah, well, I'm writing that proposal as we speak already.
Our next question is from Yako again. How much geological evidence is there for climate warming after the impacts?
Oh, Yako, with the questions. So there is and there isn't. So for some of the impacts, there is warming. In fact, after the Jigsaw Clump and Cretaceous impact, there's a wild spike, a cooling warming spike immediately after the impact. And then we get a gradual sort of warming trend for about 500,000 years afterwards. So that's sort of what we would predict, actually, with this destabilizing function in the atmosphere. But the issue is that the simple model that I've put forward here doesn't take into account the complexities of the climate system at different points in geological time and for different starting climate scenarios. So there are a range of feedbacks and buffers that exist now that didn't exist, 200 million years ago, for example. The continental arrangement and ocean circulation patterns change or will buffer and modulate that warming effect from solar radiation. So it's not as straightforward to say we have this hit, more solar radiation, increased warming, and that we would see that in the isotope record. We might not. So this is another line of inquiry that I would love to pick up and run with, really engaging with the paleoclimate community to explore what's possible with this mechanism and how it might influence global climate scenarios in the past.
Yeah, very interesting. We have another question from Valentine. Do you know if the potassium feldspar content in the atmosphere triggered by the meteorite impact can or will change the overall atmospheric circulation of the Earth, as in changing the dimensions of like the Haley cells, for example?
Yeah. There's no evidence to suggest that the mineralogy of potassium feldspar itself could change atmospheric convection. But what it would do is, because it affects cloud formation and the development of ice particles, those clouds are different composition at different altitudes in the atmosphere, and that will affect atmospheric circulation, particularly in the troposphere and in the mid-latitudes. So I suppose yes, actually, is the answer. I'm saying, I said no, I mean yes. Yeah.
Okay. Our next question is from Stephanie again. Just one second. The Permian Triassic boundary, the Jurassic boundary, and the Cretaceous Paleogene boundary are all associated with these huge, large igneous provinces. Is this a coincidence? So basically, do you think the impact craters create the large igneous province?
So I think that, and we went around the houses on this in the review process, because just like meteorites, large igneous provinces do not always correlate with mass extinctions. And indeed, the largest igneous province does not correlate with a mass extinction episode. In fact, doesn't correlate with increased extinction intensities at all, right? So what I'm saying here is that it is curious that our analysis of potassium feldspar-rich ejecta blankets always coincide with mass extinctions, and they are always present when lips are associated with mass extinctions. So the way I see this working is that the potassium feldspar affects the clouds, it destabilizes the climate. Well, it makes the atmosphere more sensitive to warming from greenhouse gas emissions because the clouds can't buffer it anymore. So what this would do is it would make volcanic emissions that might have otherwise been benign lethal, generating global warming or climate destabilization that would otherwise be buffered by cloud feedbacks and whatnot. So that would be my take on it, that LIBs will be enhanced by these K-feldspar rich ejecta blankets.
Yeah, a very disastrous feedback cycle.
Yeah, catastrophic interaction. Yeah.
All right, well, thank you everybody for your great questions. And thank you again, Chris, for your awesome talk. So make sure you tune in next week as well at our regular time, so 4 p.m. UK time for our next talk, which has yet to be determined. So stay tuned to Twitter for what we'll be talking about next week.